Sitting comfortably, because this is probably going to be one of the most impressive talks of the conference. I feel myself. This is a talk by Philipp Haller, and I did some research on Philipp, and I came up with quite some impressive numbers and facts. First of all, he's the author of the Scala Actors library, as many of you will know. But then I looked up all his scientific papers, and it turns out he wrote 51 scientific papers since 2008. Or maybe, he's not the only one called Philipp Haller. But I'm just going to go with he wrote 51 scientific papers. And the most cited paper, the most famous paper by A.P. Haller, co-written with Martin Odesky, is cited 301 times. And it actually does introduce the Scala Actors paper, which I think is really impressive. He is the top 10 contributor, well, a top 10 contributor. I guess, there's got to be 10. He is a top 10 contributor to the Scala project itself, and he is here to talk today about concurrency in Scala. So I would like you all to give him a very warm welcome. Ladies and gentlemen, Philipp.
All right, thanks for this nice introduction. I didn't know I was such an impressive, academic, but all right, so. I'm gonna talk a bit about safe concurrency, and in particular how to make concurrency safer via static checking at compile time, so via types, and because race conditions and so on, right, are reasons for why concurrency is so difficult, right? We have all kinds of hazards that can easily happen, and they can also be difficult to find and difficult to fix. So question is, how can one actually make concurrent programming easier? And of course, there have been lots of remedies proposed over the years. There's many programming models and libraries and what have you that have been proposed over the years to try and make concurrent programming simpler. And of course, many of those programming models exist as libraries in Scala, right? And now and I think that's a great approach to provide different programming models as libraries, because it's not actually clear which one is ideal for a particular use case or a particular class of problems. So it's good that we can actually choose, and we can develop new libraries that are quite expressive, right? However, what most of these libraries have in common is that they can't actually prevent these hazards statically. So I can still write programs that pass the compiler, and I can still get race conditions, for example, at runtime, right? And of course, that's because with libraries, you're restricted in what you can do, right? You can't just extend the language in arbitrary ways. So there are some limitations of what we can do. And this talk is about some minimal as good as we can extensions to Scala. Mostly the compiler in some very small ways that enable a number of additional static checks. Okay, so and what I want to do is just introduce a running example where basically we have, let's say, some image data which we'd like to process in some way. We'd like to apply maybe some filters to it, right? And that changes the image in some way. And we may have an image processing pipeline where we have multiple filters or multiple stages that process the image. And let's say we like to process lots of images. Then, of course, we want these pipeline stages to run concurrently, right? Obviously. And now let's let's say we have certain constraints in our system, like image data may be large, and main memory may be very expensive, right? And that is true if we have so much data to process that it doesn't fit into the memory of a single machine, then by definition, main memory is expensive for us. And so now one way to actually get a performant implementation is to forget everything we know about functional programming, right? And do in-place updates of the image data, right? So we have like image buffers that these pipeline stages directly in place change, for example, right? That's then we can avoid expensive copies, right? We don't have to copy everything into a new image buffer that has some things changed, right? We just update in place. We avoid copying, right? And also, we can pass these mutable buffers by reference between pipeline stages. I mean, if they are on the same machine, then of course the fastest way to pass around these buffers is by reference, right? And again, we'd like to avoid copying. But if we do that, then it's of course rather easy to produce race conditions. So let's say stage 1 sends a reference to a buffer to stage 2, and of course, if we do that following the send, both stages have a reference to the same mutable object, and they can concurrently access these mutable objects. And well, that's not a safe thing to do. So in this example, it's very easy, but of course there are many other patterns and situations where you can have similar issues. So, but I'd like to use this running example as a perhaps the simplest example that illustrates this approach that I'm going to show you. And the way I'd like to avoid data races in this for this running example is as follows. I'm going to use an approach which is basically to do a safe transfer of ownership between the pipeline stages, right? So like when I send an image buffer, I transfer the ownership of that buffer from one stage to the other stage, right? And of course, the sending stage loses ownership, so it will be illegal for that stage to access the buffer that it just sent, right? And we'd like to actually prevent that statically. Right, so the compiler will prevent the sending stage from further accessing objects that where we don't have ownership anymore. And what are the advantages of this approach? Well, it's nice that this does not have runtime overhead, right? Like we still do the same pass by reference of mutable buffers, right? So the extra safety that we will get does not compromise the performance, right? That's very attractive. And errors are caught at compile time. So that's, of course, also good. Now, of course, how can we even do that in Scala, right? After all, Scala was not designed from the beginning to prevent these kinds of concurrency hazards statically, like Rust, let's say. So it's not obvious at all how to do this in Scala, right? And so here's where we enter this project that we call LaCasa. And at the end of the talk, you'll also know why it's called like that. But for now, that's our name. And what this provides is essentially affine references. So these are references that we can transfer between concurrent processes, for example. And of course, there's for these transferable references, there's at most one owner per transferable reference. Yeah. And now, how can we provide these references? And there are actually two ingredients that we use. One is access permissions. So the way we'd like to do this is to say, well, if I have a mutable buffer that I'm sending between two stages, then a stage is only allowed to access this buffer if it has an access permission. And sending the buffer consumes the access permission, right? So the sender loses the permission to access the buffer. And the second concept we're going to use is essentially encapsulated boxes that can contain objects such as buffers and things like that. And we're going to transfer those boxes. And the permissions, they control access to these boxes. Okay? And well, so these access permissions, actually we're gonna provide them implicitly, right? So they will be in our programs passed around using implicits, which also helps keep the syntax lightweight. We don't have to pass them explicitly, right? Which could be tedious if whenever we want to access a box or something, right? We would need to explicitly pass around the permission, but with implicits we can do this automatically and while still having static checks, right? And these permissions, they have such a type, can access, with a type member C, and this type member is going to be quite crucial, as we're going to see later, and because this type member actually identifies the box that is controlled by this permission. Right, so we have boxes that are polymorphic, so we can put in different kinds of objects, and they also have a type member. And if the type member of this permission matches the type member of this box, then it means this is a permission that grants access to this box. So we'll see how this looks like. So how we match up these things. So let's say we have a method that takes a box. It receives a box, and we also want to pass the access permission to the box, because otherwise, as we'll see, it's not going to be possible for us to use the box in any way. So we also need an access permission, and like I mentioned, we use an implicit parameter for that. And this permission now says, well, this magical type member here is equal to box.c, right? So this means this is a path-dependent type, which means this access permission is really specific to that particular box reference. There's no other box that matches or can be controlled with this permission, right? It controls exactly this box and no other box. So the only there's only a single box that has this type that also the access permission has here. Okay, so the compiler actually statically ensures that references are disjoint or separate and so forth, right? So we leverage that, and now let's see how we actually create boxes and permissions, right? This method that I showed you just received a box and a permission. How do we create these things? And here we choose like a very simple example, right? We just have like a message class that contains some mutable things. It has a var, and that's an array. It's like terribly mutable, right? And let's say we want to put this into a box to transfer between stages, right? Well, what we do is we basically use this make box method and tell it how to initialize the box, like which object you want to put into the box when you create the box. Okay, so this MK box is provided by the LaCasa library, right? But then what happens is we have this closure, which takes a parameter packed, and packed means it's basically contains both the box that was just created and initialized with a new instance of message, okay, and the access permission, right? So we can actually pull out the access permission here, make it available as an implicit, and the box is also available as a member of packed, right? So we have both things available now, and so that means we can then access the box and so on. So The next thing I'm going to show you is how to actually access a box once you have one and a matching permission. But first, I can also show you packed, right? So packed is basically just has two fields, and they actually express the same thing, where the access permission is specific to that box, right? Otherwise, of course, this would not be useful, because we need a compatible access permission for that box. All right, so then how do we actually access boxes and use them and so forth? Well, these boxes are well encapsulated, and so we first actually have to open them for access. So we can't just we need to use actually a specific method for that. There are several reasons for that I'm going to get into. But basically, we just say, well, the box, open, and then we have a closure that we can use to access this object of type message, right? So MSG is type message, so we can operate on that object. Yeah. There are some restrictions what this open can, what we can do within this closure. So, for example, it's not allowed to capture mutable objects by this closure, right? Because otherwise we could just leak. We could just store a reference to some part of this message object. Like we could leak a reference to the same array to the outside, and that would breach essentially the encapsulation of the box. So that's not allowed, right? So basically, what LaCasa also does is, check this closure to make sure it actually only captures immutable types. Okay, that's important. And of course, I can only open a box if I have the matching access permission. So the open method takes an implicit with the permission type that matches this box. All right. So now, how do we actually transfer a box? Right. We need to transfer the ownership, and transferring ownership consumes an access permission. Right. So let's say we have two actors or some other processes. What we want to do is, once we have our nice box and we've put something in there and so on, we now want to send the box over to some other actor, right? Something like that. Now what we actually want is that this box is like, it's illegal to access the box afterwards. So we'd like actually to statically prevent people from accessing the box afterwards, right? Now this is a bit difficult, because once there's an implicit in scope here, this implicit access, well, it's also in scope following the send, right? After the send, it's still in scope, so we still have the permission, right? So the question is, how can we actually consume the access permission, right? And that's basically what we need to do, is we need to make the implicit permission unavailable in the continuation of the permission consuming call, right? So send consumes the permission, and in the continuation of send, the permission has to be made unavailable. Now the continuation in the previous example was implicit, right? It's just all the code that follows this call. That's the continuation, right? It's even the code, it even goes further down after the make box and so on, right? So continuations are typically implicit. But since we need some control over what the continuation can do, we reify it, or we make it explicit. So what we do is we use continuation passing, okay, as a way to have control over the continuation, right? And that's actually necessary because, well, Scala's type system is flow insensitive. So the control flow is unable to change, which implicits are in scope or what the type of things are, etc. So we can only change type information by entering a different scope. For example, the scope of an explicit continuation, right? And then once we have that continuation explicit, we can restrict it to exclude the consumed permission, right? That's what we want because that has been consumed. So how does this look like? Well, essentially what we need to do is that we need to change our send operation here to take first a continuation here, which is just, this can just be a nullary function, so just a block of code, right? But it has to be there so that we can look at it and make sure this access permission is unavailable, right? And okay, so let's say we have this continuation. How do we actually restrict the continuation? And well, essentially what we actually need to do is, since the continuation is just a closure, so it can capture things, including implicits, etc., from the enclosing scope. So what we actually need to do is we need to disallow capturing variables of certain types from the environment, right? And for this, we can actually leverage something called Spores, which is a spore is essentially a closure that allows you to restrict the environment. So I'm just going to first show you how we need to augment the type signature of send to allow that. So first, of course, we're sending a box here, and the continuation now has to be a spore that we will restrict, right? So we're restricting the spore to say, well, this is a type that's excluded from occurring in any captured type. So this is because we're consuming this box, right? And so this type member should never occur in a type that's captured in the spore, because if so, we could also capture the permission and continue accessing the box, right? So this is one thing we do. And then we also, of course, need the implicit access permission, because that's the thing we need in the first place to be able to consume the box, right? And that's the same thing as before. Note here that this method now has return type nothing, because actually this is not going to return, right? So for safety, we need to make sure this explicitly provided continuation is really the full continuation, like there's nothing else happening after the send. Because if there would be anything we could do afterwards, we would again enter the scope where the implicit permission would be in scope, which we can't allow, right? So this has to be a non-returning function, a non-returning method, actually. So let me just clarify what we do here with these spores. So a spore is essentially a closure that has an explicit environment. So whatever you capture is actually explicit. And what's interesting is that you can give these spores, or these spores are given function types that are refined by the types that are captured. So you can actually, let's say we create a spore like this. So this is really just like a closure, right? And it captures this MSG here, right? And we capture it, and now we have it available locally as variable s, and then can use it, right? So we're just capturing one variable of type string here. And what actually happens is that the type of this expression, of the spore expression, is a spore from into string, where type captured equals string, because that's what we're capturing, okay? So what's interesting is that the type actually contains the information about what we're capturing, right? And that's nice, because we can then further refine this and say, well, okay, this capture type member is nice, but we could also have a type member excluded, which tells us which types are not allowed to be captured, right? That's what excluded does, and I'm going to show you how this comes into play. Essentially, we want to convert regular closures into spores just based on expected types, right? So we want to implicitly convert function literals to spores. And of course, at compile time, we check whether that's valid to do. That's a valid thing to do. If it's not valid, you get a compilation error, right? So, but the nice thing of doing this is that, first of all, we have a more lightweight syntax, so we don't have to write spore and then a block and so on, right? But we could just implicitly convert a regular closure to become a spore. And but we can also then check these excluded types. So for example, let's say we have a type that we call safe spore. It's safe because we exclude certain types from being captured, right? So we define our safe spore type to be spore A to B, and where the type member type excluded equals some excluded type, right? Well, now we can use this safe spore type over here and assign a regular closure to S, right? And so now the expected type is a spore type, right? And but we're providing a function type, and so the implicit conversion kicks in, and which is actually implemented as a macro. So the implicit conversion macro kicks in and goes ahead and checks the closure to make sure it does not capture this excluded type, right? If that's successful, we get actually an instance of this type, right? And the compiler has checked. We've checked at compile time that this this constraint is satisfied. Right. So let's come back to our example here. So what we need to do here is when we consume the box in this continuation, which is a nullary closure, we simply implicitly convert the nullary closure to a spore that excludes the type that controls the box and the permission, right? That's what we've seen in this complicated type signature previously, right? So that means that the syntax actually doesn't have to change. I can write it just like a nullary closure, but we still get the compile time check that we're not actually capturing the access permission, for example, right, or the box, and so on. So it is consumed, and we check it statically. So now there's one more problem, actually, that we have to tackle, which is that it's actually not actually safe to transfer all types. Here's a very simple example. So let's say we take our message class again, and we add a method leak, which leaks our array to a field of a global singleton object, right? Well, this is a bad thing to do because this is a global singleton object, which means clearly the sender can access it. It's a top-level object, let's say, right? The sender can access it. When you transfer this message to the receiver can invoke leak, which also accesses that singleton, and you have a data race, right? So that's not desirable. So what we need to do actually is we kind of have to restrict the types that we can put into boxes, right? And we need a list of requirements, which is not actually that complicated. I mean, we basically have to make sure that methods only access their parameters and this, right? That they don't actually access some global state or some enclosing object that gets implicitly captured and so forth, right? And while these are actually the kind of methods we would predominantly like to see, right? They shouldn't access things outside of their scope so much, except if it's the field of this, right? Of course, they should be able to do that. But we also need recursively that these methods only instantiate safe classes. So a method should not be allowed to instantiate a class that itself accesses a global singleton object, right? Because then we could indirectly have another one of these leaks. So these methods, in turn, have to only be allowed to instantiate these safe classes. And of course, the types of the fields also have to be safe, right? And what's interesting, though, is if you look at these rules in more detail, which we've done, you find out, well, what we're doing is we're actually checking whether a class, let's say, conforms to the so-called object capability model, right? And the object capability model, if you haven't heard about it, I encourage you to actually look it up, find out what it is, because this is widely used in the JavaScript community to restrict JavaScript code so that it's nicely sandboxed. So let's say you have, you're loading JavaScript code from a third party. This JavaScript code should not be able to touch anything on the website except for whatever, the ad or whatever you're displaying, right? So you need to have secure sandboxing, and that's what the object capability model provides, and this is what we're checking. The really cool thing about this is a binary decision, right? We can say, well, a class conforms to this model or it doesn't. So it's really just a 1-bit information we need per class. And if a class conforms to this model, we can put it into boxes and we know that it's safe, right? And of course, now the question is, well, people haven't really used object capabilities in Scala so far. So how can we tell whether this is a practical way of doing things, right? And to find out, actually, what we did is an empirical study where we just looked at some larger projects, including the Scala library and other projects, to see, well, which percentage of their classes or traits actually conform to this model, right? And turns out that, well, I mean, depending on the kind of project, you do have between 20 and 65% of classes actually already conform to this model, right? So it's already lots of classes conform to this, so we can just reuse them unchanged, right? We don't even have to touch these classes. So that's very good. And this was actually a very simple object capability checker which could still be refined. So for example, if you look at the collections library in Scala, well, they actually make use of singleton objects, which are perfectly safe to access, because these singleton objects don't have state, right? Like if you have stateless objects, they are safe, right? And these are quite common in class libraries. So these percentages, we expect to actually increase, and we actually did some experiment where we sort of marked certain singleton objects as safe, those in the collections library, for example, and others, and then actually these percentages, of course, increase further. So we're actually quite confident that this is quite practical to do. So let me maybe summarize what we're doing in LaCasa. Well, basically, we have these encapsulated boxes, right, where the main insight is that we use the object capability model for alias protection, right, to make sure that state is not leaked to global singleton objects, for example, right? And then we use access permissions that we implement via implicits and path-dependent types, right, to match access permissions to boxes, and thereby we can statically check whether the permission is available. And as I've alluded to or intuitively shown you, is that we can actually statically prevent data races. And we've actually developed this pretty far and have also mechanical formalization of these things as well. So one thing that I didn't show you actually, which is interesting, is that you can also store these boxes in the heap under certain circumstances, right? So let's say I have an actor or a stage in a pipeline that needs to keep a box around for several messages that it receives, let's say, right? Then it would need to store that in the heap, between message handling, right? Handling several messages, right? And that requires us to store boxes in the heap. And this is something I haven't shown you, but we support this as well, in particular for things like actors that are not actually aliased, in contrast to actor refs, let's say. So we can do more things than I've shown you. And there's lots more details. There's a paper that's going to appear at the OOPSLA conference, but you can also look at this tech report if you're interested in more details. And like I mentioned, this student of mine has actually formalized the type system and operational semantics and so forth in Coq as well. Okay, so what is the status here and what are plans? Well, we have a prototype implementation, right? which consists of both a library component and a compiler plugin. The compiler plugin is mainly there to check object capability conformance, right? Which is not actually that complex, right? And otherwise, as I've shown you, we actually leverage things that already exist, like Spores and things like that. And we also have like some strawman code to like, okay, how would you integrate this with actors, let's say, right? And that's what I've shown you, where I have this funny send method with this more complicated type signature. But what we actually want to do is like have real adapters that are really usable for real projects like Akka and others, right? So and then of course we actually want to also do this for .t. And here what's actually interesting is that there is some work that Martin actually has proposed earlier about implicit functions and like implicit function types, which can actually allow us to simplify some of the API. So I've showed you this mkbox method, which takes a closure, and the closure takes a packed parameter, which contains both the box and the permission. With implicit function types, this can be made nicer, actually, right? So this would be really nice to explore in .t. All right, so I'm at the end, and if you have any questions, open to that, and thanks for your attention. Yes?
If you have any methods that contain such a send call, which will then need this implicit access token, it will have to also be able to consume that token, which means that you would need to pull this trick of making the continuation explicit and changing the return type to nothing for the enclosing context. That's quite some boilerplate, right?
Right. So maybe I repeat the question so it's recorded. So Roland stated that if you have a method like send, which takes an explicit continuation and does not return, then it means that whatever method calls the send method, like also has to, provide the continuation and is also not allowed to return, right? So and that the question is, well, doesn't that lead to a lot of boilerplate, right? And indeed, basically the consequence of this model is that you write your code in continuation passing style, which, well, some of you can perhaps do that, but it's rather tedious, right? And now what we've been doing here is to say, well, if you have an adapter for Akka, let's say, then you can actually, what you can do is you can still write your def receive in the way you're used to, right? But wrap it in a way where you have this trampolining thing where you can have a send inside, but it at least you don't have to change your receive method, right? But of course you still have the issue that if it's not directly inside the receive method, you still and it's inside some other method. Yes, you do have to write continuation passing style, so there is still some boilerplate. So that's true, and actually, our plan to really attack this is to use something like coroutines, which is similar to async await that Alex Prokopets is going to present later today, right? Actually, right after this talk, I think. So to actually say, well, okay, this system does the type checking, right? And with coroutines, we're actually now going to transform the code in a way where you don't have to write continuation passing explicitly. So that's the idea. Now, this hasn't been done yet, right? So we are expecting that this still requires some good ideas and so on. But it seems like it should be feasible, and that's the idea, basically. And the main reason why we actually have this continuation passing style is, like I mentioned, well, Scala does not have a flow-sensitive type system, so that's the thing, right? That's the main reason. But yeah, Miles.
There's a really nice continuation passing style
Right. So Miles mentioned that there is actually a very powerful continuations plugin for Scala, right? And whether we've looked at leveraging this plugin to do this CPS transform. And the answer is, well, we actually have not looked at it yet, but it definitely would also be good to look at that, right? I mean, the question is like, what's the best solution? And we just don't know yet, right? So I'm well aware of the continuations plugin in Scala, definitely, and yeah, it's future work basically for us to figure out what's the best way to then do the CPS transform. But the nice thing is, like, you can use it, like you can run stuff. You can, you know, we have examples using actors and whatnot. Like it's usable, right? And if the logic, if your concurrent logic inside an actor or a concurrent pipeline stage or whatever, if that's not too complex, it's actually feasible, right? It's just, of course, that, you know, in the more complicated cases, yes, it can be a pain, I think. All right. Yeah. Yes.
One problem with the continuation parsing style and the plugin that Miles mentioned is that the types can get really confusing pretty
Right.
quickly.
Yes.
Especially if you try to do generic programming and so on, and you try to use abstractions, God forbid. That seems to be a common theme, though. That tackling this kind of problem really gets nasty. That's the same problem exists in the Puni language. So it's not really clear how this shall be tackled. Have you also compared the concepts to, or the consequences of your choices to perhaps a type state-based approach?
Right. Okay. So this was a two-part lecture. No, sorry. This was a two-part question. The first part was, well, the continuations plugin in Scala. One issue with it is that the types can get fairly complex pretty easily, which can hinder. It can be a hindrance, right? And I'm quite aware of that as well. That's actually one reason why things like async await exist, and probably also Alex's coroutines, which I want to learn more about, to actually keep the systems or keep the types that happen, that occur, that are inferred, and so on, simpler, right? Like async await has no effect on the complexity of your types. There is no complexity because it's just futures and promises, and all you do is a CPS transform, and the types don't change, right? So yeah, that's actually intuitively why I've talked to Alex about perhaps leveraging something like coroutines, because like the main thing we do is really restrict the implicits, right? So it's a kind of particular kind of restrictions that we want to enforce, right? So yeah, but again, we still have to do that. Your second part was type state, right? Have we explored type state as an approach to do that? And yeah, I'm actually quite well aware of type state oriented programming. There have been prototypes also for Java and things like that. And actually, if you go read our paper, we do actually discuss. We have a section where we discuss also approaches like type state and how they compare. And it's certainly interesting, but type state means that well, the flow of your program, like the type state can change in the flow of your program, right? So the type state is dependent on the control flow, and like I mentioned, it's really non-trivial to realize this in Scala because it's just fundamentally flow insensitive, right? So yeah, it's really not clear how you would do it, but I mean, I agree. If you would have such a type state tracking mechanism, this could be quite powerful, right? So I mean, I think that's an open research question, basically. So okay, thanks again.